Hawaii represents another kind of problem because the last 14 years, Kilauea has remained in outgassing stage, which means there is a lot of gas coming out of the volcano, and the the gases which are coming out of the volcano will react with the air, and that results in a plume of volcanic smog, what we also call VOG actually. The VOG volume is composed mainly of water vapor, but there are also sulfate particles. And these low particles are so teeny tiny that actually you can breathe it in, and it can be a problem in your lung. And it causes a lot of allergy, especially when the humidity is high. So it could be a problem. Okay, now from this slide you have to know everything. So far you really have to know the gases, what kind of gases are in the volcanoes and what kind of problems can it cause. But from the lava flow you really have to know. I asked these questions: what kind of lavas are come on, you have to understand, and I am going to explain why, but most of the lava flows on earth are going to be basaltic. And remember, basalt is what is basalt? Okay, it's mafic, means that the SiO2 content is between 35 and 45%. Remember, you are on the top part of the bounce reaction series, like up here. So that's mafic. Now remember, the SiO2 content is like from 35, it goes from 35 to 65%. 65%, and that's the SiO2. And the temperature up here is between 12 and 11 to 1,000 degrees. So the temperature is really high. And if you think about the viscosity, remember, the higher the temperature, the lower the viscosity. And also, if you think about the SiO2 content, as I said, is going from 35 to 65. I already said that the temperature is 1200 and probably 1000, but rather 12 to 11. So it's high temperature, which makes viscosity low. And the silica content is relatively low, which also helps to have low viscosity. When the viscosity is low, that means the lava is very water-like, so it's flowing fast. Therefore, it's much better chance for mafic lavas to actually reach all the way to the surface. So that's why most of the lava flows on Earth are basaltic. And when I say basaltic, or when I say mafic, it's synonym. Mafic, basaltic. You can use the word mafic or basaltic. It's synonym. Mafic or basaltic. Synonym. Don't forget that. Even in historical geology, I will refer to this. So this should be a long-term memory. And actually, really, this is something which is important to understand if you happen to move somewhere where there are volcanoes, if you should be scared of them or if you should be okay. So now, if the lava is really fluid, remember, even if there is gas in it, it's going to just escape really easily. So therefore, these volcanoes will be very friendly. They are not going to be explosive. They usually have a lot of lava. That means that they will flow far away, and there is usually high volume of lava flow. On the other hand, if we have phasic lava, I can also call it rhyolitic. So rhyolitic or phasic are synonym. Rhyolitic. Now don't forget, when you have this, then we are in the lower part of the bounce reaction series, where the SiO2 content high, the temperature is low. So what kind of viscosity these lavas are going to have? And it says right there, so you can read it. But because what I just showed you, the lower part means higher SiO2 content and lower temperature, both of them are going toward higher viscosity, which means it flows like honey. This is very important because when it's like that, and I want you to pour the honey, and I'm going to probably make it in the lab for you to do it. So I'm going to make you to flow honey. So you flow the honey, and I want you to see what happens with the bubbles, which are in the gas bubble, which are in the honey. Will they come out easily? No, they will actually come up like basically the gas collects, and then the pressure builds up and then it explodes. But of course not in the honey, but in real life it's more like that. So when you have low viscosity and the gas content is high, you're going to have explosive eruption. And a lot of the time, because of the gas, it disperses the volcanic material, and actually it will produce pyroclastic flows, which are really, really dangerous. There are cases when actually the phasic magmas can degas, and they can erupt lava in manner which are not eruptive really badly, but it's much less common. So most of the time when you have phasic or rhyolitic lava, it's going to be a very explosive eruption. So now we're going to talk more details about the mafic or basaltic lava. Remember, the mafic is a synonym. I just said it, told you, mafic. So these lavas can be subdivided into two end members in terms of structural type. And one is the Pahhoe. When you have a Pahhoe, that means it's fluid, but it does have some gas. So therefore the surface of it is going to be very ropey. The other one is the which is viscous, more viscous. I mean, you know, it's in the mafic lava, so therefore it's just a little bit more viscous. It has less gas, and therefore it will have this really sharp broken surface. The name comes from the native people in Hawaii, because they hated to run on this lava because it really hurted their feet, so that they didn't have shoe. That's why they call it you know, as they were running on it. The next one is the pillow lava. The pillow lava is strictly lava which is flowing into the water. So these are underwater volcanoes around the mid-oceanic ridges. But also, you know, like if you go around Hawaii, there will be a lot of pillow lava. So mainly the name just means that the lava went underwater. And when it does, it cools down instantly and takes up the smallest shape possible, which is the sphere. So these are like spheroidal kind of shape lava, which goes underwater. So no, pillow lava always goes underwater. So this is Pahhoe. This is on top of this is Pahhoe, and that's the you can see these rugged surfaces. That's So and I'm not even going to try write down the Pahhoe, so don't worry if you misspell it. I won't take points off of it. And then here is the pillow lava. It's very typical, the round surface. So anywhere you go somewhere and you see this kind of pillows on top of each other, you know that this went underwater. So it used to be pillow lava. And this is a beautiful picture of pillow lava on land. So you know that at the time when this lava formed, it was underwater. And this is a typical non-explosive mafic eruption. And in Hawaii and everywhere where you got mafic lavas, this is how the eruption happens usually. It's very very smooth, the lava just flowing away. It's not a big deal. Usually people don't have to be evacuated or anything. It's gonna be fine. So Hawaii is this kind. It can cause some allergy, but that's about it. Now some of the surface and internal features which these lavas show is pressure ridges, which are typical. The next slide will have pictures. It's typical buckled area on the surface of the lava flow. Then you got the spatter cones, which has little cones. I'll show you in the next one. And most commonly the columnar joints, which is very characteristic to mafic magma or basalt lava. These are parallel fractures that form perpendicular to the lava surface as the lava flow cools and contracts. You know, it just from the fact that it gets smaller and makes these cracks, which are always vertical, and it's very, very typical, and it's only characteristic to mafic lavas. And then you have the lava tube, which is as the lava flows on the surface, it makes a crust as it cools, and underneath of that crust, the lava is still flowing, and when the last of the lava flow out, you're going to end up with a lava cave. I'm going to show you. So this here is the pressure ridge. This is the splatter cone, very typical. And this is the columnar basalt. And here you can see the Devil's Tower in Wyoming, which is typical basalt columns, the columnar basalt. So from a distance, and I want you please to remember this, anytime you see something like this, you know that it's basalt. And this is the lava tube. Lava tube is really amazing. These are not stalactites or anything. These are usually plants because it's very close to the surface. These guys are always going to be very close to the surface. So as the trees roots are growing, usually they go through. So you'll never find stalactite or stalagmite in lava tubes. Usually the people walk on the last lava flow, which went out. Now, these mafic lava flows are so safe that basically as soon as it makes crust, you can actually walk on it, and you can take samples from the hot lava under that crust. It's really cool. I would do it anytime. You know, I went to Hawaii once, and I was standing pretty close to where the lava went into the ocean. It was an amazing experience anyways. Now, the next one is the endocytic lava, and we kind of already talked about it, that it's more viscous. It will produce blocky lava. The surface will contain smooth-sided angular fragments. Those are the blocks which were thrown out from the volcano. And they are not as vesicular as the lava fragments. The blocky nature of these flows is the result of higher viscosity andesite. And they sometimes are thick enough to make lava domes, but most of the time they are not. They usually will erupt from stratovolcanoes, where they form a small amount of lavas and then a lot of pyroclast. The lava usually, because it's more viscous, will not go far away from the mountain. It's gonna stay right there because it's high viscosity, so it won't flow really well. Usually the endocytic lava will not make huge amount of lava. It's going to be much less than the mafic one. And that's a typical picture of the endocytic lava flow right here. See, it just only went down on the mountain, no further. And the last one is the rhyolitic lava. The rhyolitic lava is like the most phasic. We are really on the bottom of the bounce reaction series. So this lava is so viscous that it really will not go anywhere. Most of the time it just makes a so-called lava dome right here. So these really do not go anywhere. Very many times the volcanoes producing pyroclastic materials, as I just told you, depending on the pyroclastic material, also called tephra, or pyroclast, also called tephra. So those are synonym, don't forget. Tephra, pyroclast, synonym. Oops, I pulled myself close. Here we are. So depending on the size, we classify them differently. The ash is the smallest grain size. It's like less than 2 millimeters. The bad news about the ash that you can breathe it in, And when you look at the ash under a microscope, they are very sharp, like volcanic glass pieces. So it really makes concrete in your lung, and it can actually kill you. So that's the most dangerous, basic. Of course, the bigger ones can hit you in the head and kill you. But anyhow, the ash is the smallest grain size. The lopili is 2 to 64 millimeter. 1 inch is 2.45 centimeters. So you can kind of calculate it over if you want. And then the bombs are the biggest ones. They are bigger than 64 millimeters, so that's 6.4 centimeter. That's about, the bombs are about 3, 4, 5 and bigger inches wide. And this is a picture of these guys. So you see that's a 10-cent piece right there. So these are the bombs, the lopilis, and the volcanic ash. The volcanic ash is right here. You see it's like a flower, and the lopilis are teeny tiny like peas. And this is a typical, you know, not a big time pyroclastic eruption, but you can see this is how the volcanic bombs and the lopilis and the volcanic ash is forming, like when the volcano erupts, pyroclast. And this is a volcanic ash accumulation in the Lassen volcanic field. No, sorry, it's Santa Maria volcano in Guatemala, but in the Lassen in California you see the same kind of thing. This is a volcanic ash which came out of the volcano somewhere down there. So you can see it's pretty thick. If you go to Oregon, there was a big volcano, Mount Mazamata, which produced Crater Lake. I think I'm going to talk about that later. And if you go to the Oregon coast, actually even almost like all the way to the coast, you can see like 4 or 5 thick, 4 or 5 feet thick volcanic ash, just like that. Now this slide is very important because I kind of want you to know this is just a summary table showing you all these important things. So here is the magma type, the temperature, viscosity, gas content, and eruption style. Sorry for the mess up with the spelling. So when you got Mafic volcano, remember the SiO2 content, actually it's like less than 45%. The temperature is about 1100 at least. Viscosity is low, we said that. The gas content is low, so the eruption is going to be non-explosive. Non-explosive. Remember, this is going to be around mid-oceanic plate boundaries, the hotspot volcanoes. So the rift, any continental rifting will belong to this category. Then you got the intermediate volcanoes. They have about 60% SiO2. The temperature is around 9 to 1000 degrees Celsius. Viscosity is intermediate. Gas content is intermediate. So the explosivity is also about intermediate. I don't want to leave around there. You know, it's kind of dangerous. When it does come, you better move away. But the worst is the felsic. The SiO2 is like almost 70%. The composition is felsic, around 800 degrees Celsius. Viscosity is very high. Gas content is high, so extremely explosive. Extremely explosive. You definitely don't want to be close to those guys. Now this slide shows you big eruptions with large amount of pyroclastic flows, and you can see the worst ever was Yellowstone. We call Yellowstone a super volcano. The 2.2 million years ago eruption produced 2,500 cubic kilometer. Remember, Mount St. Helens made 1 cubic kilometer, and it was pretty devastating. So 2,005 times more pyroclast. If this happened again, just about everyone in the US would die. I mean, no question. If not because of the eruption, we would die because we wouldn't have any food. If this guy came and all the aerosol in the air would cover the earth, we would have volcanic winter like for 10 years or so. So it'd be pretty bad. Yellowstone also erupted 1.2 million years ago, at that time only produced 280 cubic kilometer. It was still pretty big. But 0.6 million years ago, it produced 1,000 cubic kilometer. So this guy was the super eruption, actually. That's when like almost all of the magma chamber emptied. If you look at it, Yellowstone 2.2, 1.2, and 0.6. So it seems like we could almost say that Yellowstone is overdue for a super eruption, because if you divide the duration differences, you're going to get like 650 to 700 million years as the eruption cycle. Anywho, the 1815 Tambora erupted 150, which is 150 times more than Mount St. Helens. And then Mazama, Mazama, the one which made Crater Lake, erupted 75. And I told you that volcano, where is Mazama? Yeah. That volcano, like at almost the beach, I could see like about 5 feet thick volcanic ash. So that is at least like 50, 60 miles away from Mazama. So that was a pretty amazing eruption. And then the Krakatoa didn't make much aerosol, but it did 18 cubic kilometer. And then the Katmai in Alaska only did 7, and it made 2 years of volcanic winter. It's crazy. So anyhow, you don't have to know these numbers. It's just interesting. So you understand more what does the amount of pyroclast means. The more the pyroclast, the more it gets up to the atmosphere, cools down Earth, producing acid rain, which kills the plants, the animals. So it's going to have very bad influence on all the living things. And if you think the last super eruption at Yellowstone, there was hardly any there were humans, but it wasn't that many as we have now. So now it would be amazingly devastating results if Yellowstone erupted. We're going to talk more about it in the lab. And again, these are the parts of the volcano. You have the magma chamber down here. That's the volcanic vent. These are going to be small little parasite volcanoes. Crater on top. This is where the lava comes out. When the lava finished erupting, most likely this will collapse into the empty hole, and then the crater gets bigger. When it's 2 miles in diameter, it's going to be called caldera. And this slide shows just exactly the caldera formation. And I really have to stop right now because I'm 22 minutes. So bye for now.